So the title is a bit of a mouthful, but I'll try to explain. Let's start with a pretty easy starting point, which is the Makai correspondence for finite subgroups of SL2C. So we'll consider this cyclic group in its matrix representation. Oh, I can't point at anything, I think. Oh, maybe this. Okay. So we have these diagonal matrices, and we have epsilon sixth root of unity, and this is a subgroup of SL2C. Something that you can do if you're an algebraist is to consider its irreducible representations. There's 6 of them. We denote them row 0 to row 5. You can form what is called its Makai quiver. So the vertices of this quiver are going to be the irreducible representations. And then, again, you fixed V this two-dimensional representation here. And then you can tensor this with all of these row i's. And this is another representation, which you can split into a sum of irreducible ones with certain coefficients. And now I'm just telling you that there is this coefficient number of arrows between row I and row j. A quiver is an oriented graph. What I drew here is obviously a non-oriented graph. But I'm just taking a shortcut, and I'm telling you that each of those edges is, in fact, 2 arrows going in opposite directions. No, V is, yeah, okay, it's this. Is that matricial? Okay, that's very important. You don't have to focus on just who G is, because G is just mu6, basically. But you have to fix an initial representation. Okay. So something else that you can do with this group is to think about the fact that it acts on C2 by multiplication and form the quotient. Okay? This is going to be an affine variety, which is going to be singular at the origin of C2. And it's a well-known hypersurface singularity. We can even write its equation inside of C3. Okay? When you have a singular variety, what you think as a rational geometer is, okay, how do we get rid of this? And the way you do this here for surfaces is very easy. You simply resolve it, and you get these 5 exceptional -2 curves that intersect in this way. You can represent this as a dual graph in this way. Each node is an irreducible component of this exceptional locus, and if 2 of them intersect, then you draw an edge between them. And of course, the classical observation of Makai is that if you look at this graph here, ignoring the trivial representation, and you compare it with this dual graph here, you get the same thing. And you don't get the same thing only for this particular G, but you get the same thing for all singularities of type ADE, so all canonical surface singularities, okay? And this is called the Makai correspondence. So I just wrote it here in more words. There is a bijective correspondence between non-trivial irreducible representations of a group and exceptional divisors of the minimal resolution of the singular surface. Okay? So far, so good, hopefully. So we're moving on to dimension 3, and see we're trying to see the situation in an easier case when this is finite. And we'll sort of be driving towards finite and abelian in our analysis in the next few slides. So, okay, in dimension 3, there's no unique minimal resolution. Since we're in SL3C, the resolutions will be crepant, just like in the previous talk, so you're all specialists in that now. So basically, we're asking, is there a crepant resolution which makes sense in the sense that it corresponds to irreducible representations of G. And the answer is yes. So Nakamura did it in the finite abelian case, which is what we're going to try to generalize a bit later. But Bridgman, King, and Reid did it for any finite G like this. And this is called the G-Hilbert scheme, and we denote this by G-Hilb C3. So you have already seen the Hilbert scheme of points in Emmanuel's talk. This is kind of a G-equivariant version of the Hilbert scheme of endpoints when n is the cardinal of G, okay? But as opposed to what's happening if you look at Hilbert scheme of points on C3, this in dimension 2 and 3 is going to be a resolution of your variety, so it's going to be smooth. Okay? Okay, it's a bit tautological for me to say, but obviously this is a generalization of what happens in the dimension 2 case, in the sense that G Hilb of C2 is indeed the minimal resolution of whatever canonical singularity you have. Okay. So what else did I want to say? Oh yeah. So we also want to know how does it make sense from the point of view of the Makai correspondence, and this is called classical Reid's recipe. So this is a bit more wordy in terms of what it means, but I'm just writing what this means in terms of G abelian. So you want to desingularize C3 mod G, and this theorem, which was proven in certain cases, which was done in certain cases by Reid, but then proved by Krohn in his thesis in 2005, is that there exists a combinatorial algorithm that decorates, well, this is, okay, I should have said. So X like this, if G's abelian is going to be a toric variety. So it's going to have a fan. So this algorithm decorates the compact exceptional locus of the fan by certain representations of the group. And we will see that on the next slide in actual examples. And not only like there is this decoration, whatever that means, but this decoration also encodes information about the Picard group of the resolution. And this is, again, in some sense, another layer of what the Makai correspondence should do. It should tell you something about what the Picard of the resolution is doing. Okay, so the aim of this talk is to generalize this construction for any Gorenstein toric variety. So this was an affine Gorenstein toric variety, but which was a quotient of C3. So that means that when you look at its cone, it only has 3 rays. Okay, we'll see this right now. So here we have an example in which we have the group that contains this kind of matrices. It is also a cyclic group of order 6, but here we fix a different representation of as 3 by 3 matrices, as a subgroup of SL3C. Okay, you notice that I denote this by a 6th 1, 2, 3, because these are the exponents of the 6th root of unity that appear here diagonally. Okay? So we want to see what the Krohn-Reid algorithm says in this case. So first we want to see C3 mod this particular group as an affine toric variety. Okay, affine toric varieties are given by, of dimension 3 like this, are given by cones in a lattice of dimension 3. Okay? Since we want, again, a quotient of C3, the cone has to be generated by 3 rays. And the way we build this singularity here is by first taking the cone generated by the bases of Z3 and then introducing the point a 6th 1, 2, 3 here. So I am just depicting a slice of the cone as height 1. This is why we have a triangle and not like some complicated drawing. This is the point that I introduced. This is the point a 6th 1, 2, 3. This is the slice of the plane x plus y plus z equal 1. This point belongs to that plane, okay? And now I create the lattice that is generated by E1, E2, E3, and this is 6th 1, 2, 3. This makes other lattice points appear on this boundary of the cone. And if you know a little bit of toric geometry, you will know that lattice points means that the variety is singular, which is what we expect, okay? And you know exactly how singular it is. In particular, this one has 2 singular curves that if you cut them with a hyperplane, they look like AN curves that we've seen in the previous surface situation that intersect together on a point which at the origin looks, obviously, at the origin of this, which looks exactly like a 6th 1, 2, 3. Okay, so now we want to resolve this singularity. This simply means that I will obtain a variety which is no longer affine. So there will be many cones in whatever fan I will obtain. But there will be no singleton lattice points that remain like this. So it's basically a triangulation of this drawing. And I'm telling you that the G Hilbert scheme, the special one that I want, is exactly this guy. Okay? So the thing that we have to do now is to figure out how to decorate this in a certain way with irreducible representations of this person. There are still 6 irreducible representations because it's the same group mu6, okay? So, right. So, oh, maybe something else I want to say is that, okay, this is similar to what you've seen before as the intersection graph of E1 to E6 or whatever it was, E0 to E5, sorry, from before. But here we will only decorate this internal lattice point and these guys. So what does this represent? This person here is an exceptional divisor, so a surface, a compact surface, and these guys are P1s that appear on that surface as well. So this, after this resolution, these lattice points will also be codimension 1 exceptional somehow, but they are not compact. And we really want to mark compact things. By the way, an example of exactly this drawing that I made here was made in empiric stock when he did local P2. Local P2 can also be written like this. But instead of adding a 6, 1, 2, 3, you add a third 1, 1, 1. Okay? This is a bit more interesting as an example in this context because there are various resolutions that can appear, whereas local P2 just has 1. Okay, moving on. So, first, a little bit of what the algorithm contains. Here, they decorate. So they have a small paper in 2002 that says exactly how to build this. So they decorate each of these triangles with a ratio that is simply given by. Maybe I should write this down a little bit. Simply given by the normal vector to whatever plane we're in. So again, remember this is secretly a 3D picture, right? So each of these segments actually represents a 2-dimensional cone that comes from the origin. Each of these cones determines a plane. Each of these planes has a normal vector to it. So this ratio here basically means, so I have x squared y. This ratio basically means that the normal vector to this plane is 2, 1, 0. Okay? So it's very straightforward how to put these ratios on everyone. Once you have like a convention whether they point inside or out, in or outwards from the plane, but aside from that, it's fine. So these ratios are important because they give you local coordinates on this triangle, which is always an affine patch, and they tell you how to move from one affine patch to the other, so how to move between triangles. And they will come up a bit later. Okay. Whoop. All right. So we have to look at the group now. So you can tell what each of these row i's are just by saying how they act on this generator of the group. Here epsilon is primitive. So row I just takes alpha to epsilon to the I. You can extend this action from just acting on C3 to acting on the entire polynomial ring by doing this, the polynomial coordinate ring of C3. Okay, when you look at this action, this induces a stratification into G invariant modules, one for each representation. So for row 0, the trivial representation, the monomials that enter into, that generate S row are simply the invariant monomials with respect to this action here, okay? In the one character space, which is basically what this S row is, you put all of the monomials that have an epsilon here when you act with G, etc., etc., okay? Every monomial falls into one of these 6 categories, okay? And so now, what is the observation? The numerator and denominator in each of the ratios that I had here is in exactly one of these S row I, okay? So in particular, if you look back at, who S row was, here we had x squared and y, and they are both, they are both in row 2. And so the recipe tells you that once you have this, you mark the respective segment with 2. Okay? You proceed this way, and you mark everyone, every segment that is here. You notice that this has to do with the slope of the cone that contains your segment, because of exactly how these ratios are defined. So in particular, if you have two segments that are supported by the same hyperplane, they have to have the same marking. But this is not an if and only if situation. For example, here you have a 3 and here you have a 3, and these two segments are not coplanar. Well, it's weird to say this mathematically, but hopefully you understand what I mean. Okay, and now the recipe also has to tell you, okay, what should I, what representation should I mark this lattice point with? And in fact, Crow and Reid do a case-by-case analysis. They first limit the valency of each node, and then they tell you, okay, if this many of the same characters go inside of this node, this is what we have to do. So in particular here, we have to mark this lattice point with 5 because we have a 3 that passes through and a 2 that passes through, so these characters basically multiply to get 5. Okay, this just sounds a bit kooky if I just leave it like this. But what is happening, in fact, is that this tells you that you can have line bundles corresponding to each of these representations, row 1 to row 5. They generate pick of the resolution. And they have a relation between them, which is that L5 is L2 tensor L3. Okay? And this is strictly coming from, so this information on pick is strictly coming from the marking and not just the group G. Because in the group G, for example, you have that row 2 tensor row 1 is row 3. But there is no such relation that can appear here in any way. Okay? Sort of. So, we need to dig a little bit deeper in order to be able to generalize this. Because so far, this is sort of an algorithmic way to do it for whatever triangle that I give you. Technically, you can spit out what the marking should be and what the relationships in pick would be. But if you try to verbatim translate this to any affine toric Gornstein variety, that means that you want to replace this triangle with any kind of convex polygon. Okay? The easiest next example after the triangle is the square. So if you take the cone over the square, this is kind of the non-quotient of C3, but whatever, still an easy toric variety. When you try to write this as a GIT quotient, which is basically what this is. Sorry, not a GIT quotient, just a quotient by a group. What you get is that the cone over the square is the quotient of C4 by C star. So now G should be C star. But C star does not have it's an infinite group, does not have a finite amount of representations. So who are your markings supposed to be? So your resolution, no matter which one it is, just has one curve that is there. So you're supposed to figure it out. Somehow, the important thing to connect with here is the underlying quiver that you still have even in this interpretation. So, okay, remember you had fixed that representation as a subgroup of SL3C, right? You had that diagonal matrix here. It's still easy to compute, okay, who is V tensor, each of the of the 6 irreducible representations, whatever, and you can still make a graph. This time it's not going to be, well, it's not going to be the same graph, and it's not going to have double arrows going each way, but it's going to look like this. It's somehow a periodic graph, and it naturally lives on a 2-dimensional torus. Somehow it also encodes the relations between S rho I, not just the rho I. But anyway, so this is the Makai quiver, and in this finite abelian 3-dimensional case, it naturally lives on a torus. Okay, a remark very much in the style of Alistair King is that the resolution that you build is a moduli space of representations of this particular quiver. So what is a representation of a quiver? You fix your quiver, you fix a vector space of dimension 1 in this case. In the abelian case, all the vector spaces are going to be of dimension 1 above each of the nodes in the quiver. And then above each arrow, you fix a map between the respective vector spaces. You vary the maps, and you have a moduli space. That's it. You need to impose some stability conditions, but we will not think of this right now. Okay, so somehow there is this moduli space interpretation, even in this case where we have a very specific recipe for what we want to do. Okay, but we need to dig even deeper in order to understand fully what happens. And sadly, this means having a derived interpretation of Reid's recipe. So this actually was needed in order to prove that G Hilb was a resolution. So it's really intrinsically related with the Makai correspondence. It is actually needed. You need to understand the Makai correspondence from this kind of derived equivalence. So I will not go into detail about what this means. Essentially, here you have G invariant objects on the singular variety somehow, and here you have coherent sheaves on the resolution. You move between these two things. An easy question, I mean, easier to answer than really understanding this in any kind of explicit way, is okay. So here on the base, you have these not on the base, but on G invariant things, you have these objects that correspond to the irreducible representations. Where do they go? And if they go somewhere, can you relate where they go to the marking? And the answer is yes, you can. And in particular, they will, so these are complexes of sheaves, right? It's all like a big thing. You send this sheaf, it could land in a complex of sheaves, but in fact they prove, so Kotyskor and Logvinenko, in the highest generality for this guy, they prove that the result is actually a pure sheaf, it's not a complex. And then furthermore, they prove that the sheaf is supported on, so it's supported somewhere on Y, obviously, and it's supported exactly on what the irreducible representation marks, okay? But this is really quite strong. They don't, so for us this will be enough that the support is that, but they explicitly compute what the sheaves are, what the image sheaves are. Okay, moving on. So, yeah, sorry.
It depends on the choice of embedding of your group in SL3.
Yes, yes. You always have to fix the embedding for this to make sense. Yes. Yes, yes, yes. Okay. Any questions so far? So now we have to brainstorm. So if we want to generalize this from triangles to like random polygons, so this is what this says. Simplicial case to arbitrary Gornstein affine variety. So you have to find an appropriate equivalent to the derived correspondence. And Blokland, Crow, and Quintero Vélez did this in 2014 by using consistent dimer models as key instruments in writing this dictionary. Again, I underline the fact that you don't have irreducible representations anymore, at least not a finite number of them. You have to create some objects that somehow relate to a quiver that then relates to your resolution. Okay, and the second thing is find a combinatorial way to deduce the markings. Something that's easy to implement, more or less. And this is something that I did together with Alistair and Jesus in 2021. And again, we have to do mark points, so compact divisors, compact exceptional divisors, and compact exceptional curves. This is line segments on whatever the fan of the resolution is. Okay. Any questions so far?
Sorry, silly question. The affine variety that appears in the previous case is the quiver variety with stability condition 0. Is that correct?
Yes, that's very good. Okay, but exactly like you, kind of like what you said, stability condition 0 just gives you a singular variety, and variation of stability conditions will eventually give you.
I'm just trying to patch this.
Okay. Yeah, kind of. This has somehow to do with variation of GIT. Like you can build these moduli spaces by varying stability condition. But in this project, we will fix the stability condition so that our context is a bit more rigid. Okay, so moving on. So I have to talk to you a little bit about these guys, and I have to make a quiver appear, and then I have to somehow relate the quiver to a resolution, okay? So this is a dimer model. Our objects will again live on a real 2 torus, similarly to what happened in the triangle case, okay? So a dimer model is simply a bipartite graph. So I have a bunch of nodes that basically creates a tiling of the 2 torus. I have a bunch of nodes, they are either black or white, and that's it. Then there's a consistency condition, which you can ignore for the purpose of this talk. It's simply that you can't have these zigzag paths that are homologically trivial. Zigzag path means you turn maximally right on when you hit a white node and maximally left when you hit a whatever. Yeah. There's a stability condition. When you, there's a consistency condition. When you do something like this, when you consider such an object, there is a way, a combinatorial way, to create yourself a polygon, which is called its characteristic polygon. And now what we do is to simply consider the Gorenstein toric threefold, whose ray generators are the vertices of this polygon. And now going backwards, for any kind of convex polygon that I can find in Z2, I can produce myself, again in a very combinatorial way, a dimer model that for whose characteristic polygon this is, okay? So considering a Crepent resolution here is equivalent to the following couple of steps. So again, a Crepent resolution simply means a triangulation. Everything here is Gorenstein, whatever. So dimer models are duals to quivers, which basically means that in every one of these faces that this dimer partitions the torus into, you can put a vertex of a quiver and choose, so each tile is dual to a vertex in a certain way, and you have to choose where is your 0 vertex. So you can interchange notations for whatever numbers you put here, but in the end, who is your 0 tile or where is your 0 vertex is important, because if you remember from the simply Makai correspondence, you only need to mark things with non-zero, non-trivial, irreducible representation. So this is basically the person that is never going to mark anything. Okay, and now you build arrows between each of these vertices by simply imposing that the white node is on the right-hand side of each arrow. So this gives you this picture here. Okay, and basically choosing where the 0 vertex is here is equivalent, again in a combinatorial way that I'm not explaining in this talk, is equivalent to fixing a Crepent resolution of the polygon. Okay? And now you need one more object in order to be able to state anything here. And this is the Jacobian algebra of the quiver. So you can form the algebra associated to the quiver, which basically means that you take paths in the quiver, you can sum them up as formal sums, and you can multiply them by concatenating when it's possible. Okay, so if one path ends where the other one begins. Okay, and then you also mod out by relations that look like this. So these are paths in the quiver with tail at the head of a given arrow. Whoops. Maybe, so let's say we fix an arrow A, and we say that if you have a path like this, let's say this is P plus, and a path like this, let's say this is P minus, then P plus and P minus are the same, okay? Right. And now, once you've associated these two objects in this combinatorial way that I have not described, you obtain that the resolution that I wrote on the previous slide is a moduli space of representations of the quiver that you had on the left-hand side. And moreover, since this is a fine moduli space, it comes equipped with a tautological vector bundle, which is this T person here, which splits. And it splits into exactly as many, it splits into a sum of line bundles, and there are exactly as many line bundles as there are vertices of the quiver before. And then you set L0 to be the trivial bundle on Y. Okay. Now there's this important result by Ishii and Ueda, who tell you that you can see any path in your quiver as a morphism between, well, these line bundles, which kind of makes sense because the line bundles represent the vertices of your quiver. But more importantly, they show that there is an equivalence of categories between finitely generated A modules, again, A is this path algebra that we have, and coherent sheaves on the resolution. Okay? But we are looking for this kind of derived, and this comes from exactly T somehow. We are looking for this kind of derived equivalence because we're trying to chase objects from this left-hand side to objects on the resolution. Okay. So, sorry. So this is the equivalent to the equivalent. The quiver incarnation of the previous derived equivalence that we only had for C, for the triangle case. Okay. So now we ask the same question that we asked when we saw the other derived equivalent. Is there any way to send objects related to one of the Li, so one of the vertices of your quiver, and track it down in this derived category and maybe see what happens to its support, what's going on? Okay, and there is an answer. For me, this is not a super satisfying answer, but it is a very difficult paper, so I'm not going to be like, that I didn't write, so I should not complain. But this is called geometric Reid's recipe. So you fix a vertex in your quiver. It's not the zero vertex. You cook up some objects that are A modules that correspond to this vertex somehow. This is actually because the category of finitely generated A modules is in fact equivalent to the category of representations of this quiver with relations that are similar to this, but you don't have to understand that necessarily in order to get this. So Bloch and Kroc and Quintero-Vélez showed that the images of these objects do have support on some divisors and on certain curves. But there is this case in which this F guy is very obscure and we don't really understand what its support is necessarily. But anyway, this is clearly a step in the right direction. So using this is what gets marked in our example. So using this, you can deduce that this toric divisor should be marked with 2 and 5, where 2 and 5 are the line bundles corresponding to, 2 and 5 here, the 2 and 5 vertices of that quiver. This is marked only with 2, this is marked with 7, and this is marked with 1. So now what me, Alistair, and Jesus did was introduce a recipe that tells you how you should mark everything. So, and then we proved that it agrees with the derived expression from before, and it also agrees with what happens on triangles. Okay? But we needed to basically rephrase everything in terms of Dymor model combinatorics, basically. Okay, so we managed to obtain this in this case. So a bunch of new things happened that didn't happen for triangles. Ooh, and I'm going to finish early again. Okay, so here's what's new to the dimer case. So interior lattice points can be marked with the same vertex. So here we have 2 that marks 2 surfaces. Interior line segments can be marked with more than 1 vertex. So there's this that never happened in triangles. The marking of an interior line segment is not determined by the hyperplane containing it, which means that we have this hyperplane here. It contains these 3 line segments. Remember, in the triangle case, we had that 2 that had to necessarily mark everybody in that hyperplane. This is not the case anymore. The marking of an interior lattice point is not determined by the geometry of the toric surface. So these are 2 toric surfaces. They are both Del Pezzo surfaces of degree 6. So they're essentially the same. But they are marked by different things. This is kind of an illustration of the fact that, moduli of quiver variety GIT is a bit finer than toric GIT, which is what you would obtain by just looking at this variety. Okay, and the Euler number of an irreducible component is not bounded by 6 from above. So basically, we can't do the very explicit recipe that Croix and Reid did when they said, okay, every vertex is valency maximum 6, here are the cases. So that doesn't really happen here. It does happen in this example, but I didn't want to put like a huge toric variety here just to illustrate this. Okay, and maybe something else that I want to say is that, so at the end of our article, there are 2 conjectures, one of which, I mean, is very expected to say, which is that the derived, the geometric Reid recipe should illustrate exactly that this is the support of the phi of the LIs, or the phi of the SIs, sorry. And also, definitely thank people a lot. And also that somehow we have the same interpretation, or we should be having the same interpretation of generators of the Picard group and relations between them, that we should be able to read exactly off of this. So we should be able to see that from here. And yeah, maybe something else that I want to say in defense of this recipe is that this is an important step in having a better expression of this, and getting the combinatorics right in the triangle case was an important step in them proving and calculating exactly who the images of these objects are through the derived category. So somehow this is a necessary intermediate step to having the full Makai correspondence, clear to us in this case. Okay, thank you. I think I'm done. Oh.